Hello everyone, this is Alindote. In my previous video, I have already discussed about the theory part of the compression member. So here I am with some numerical examples of the chapter compression member in design of steel structures. See, this is problem number 1. You can read the problem from here. Here it is mentioned that ISHB 350 you have to use, and you have to finally find out the compressive load, that means the design compressive strength of the member. So first of all, we have to check the end conditions. As it is given in the question, it is restraint in direction and position at both ends. That means it is fixed from both sides. We have to go to table number 11. In table number 11, this is fixed from both the sides and the effective length is 0.65 L. So the effective length is 0.65 into L from table 11. Then we have to write all the properties of the mentioned section from SP61. Mind it, these two are the radius of gyration, but in this SP61 the radius of gyration is mentioned as RXX, but here we have taken RZZ because we are considering the horizontal axis is ZZ axis and the vertical one is RYY axis. Now we have to check for the buckling class of the member. We have to go to table number 10. In table 10, H by BF we have to check. All the values we can already find out from the properties and the value of TF. Let us see in table number 10. Yes, for I section we have to check H by BF. It is greater than 1.2 and TF is less than 40. That means ZZ along ZZ buckling class A and along YY buckling class B. See here ZZA and YYB. So by looking at this two radius of gyration, we can easily say, as this one is the minimum, so YY axis is the critical axis, YY is the more severe comparing to ZZ axis. Then RY, just because of RY less than RZ, so we can say that compressive strength along YY direction will be minimum, and that will be the design compressive strength of the member. So in this problem we can find out the compressive strength along YY direction only, but for better understanding I did it in both the ways. Write a design compressive strength along YY axis. Area you know, 9221 mm square from SP61. Slenderness ratio you can easily find out by KL by RY with this value, and as the buckling class along YY is B, we have to go to table number 9B. See, in table number 9B, yes, table number 9B, for the value of KL by R, we will get two number of values. We have to interpolate among these two. See, here it is 43.58, so we have to check among 40 and 50, FY 250. Then the values are 206 and 194. So we have to interpolate between these two values, 206 and 194. Yes, from the interpolation we can easily find out the value of FCD, 201.7 Newton per millimeter square. This is the interpolation I have shown here. So when you get FCD, then you can easily put the FCD, PD is equal to AE into FCD. This is the compressive strength along YY axis. Similarly, you can do it in ZZ axis with the same procedure, taking buckling class A. But here you can see along ZZ axis the buckling and the bend compressive strength is more than YY axis. So that's why we can say that the design compressive strength of the member is the minimum one, 1859.8 kilonewton. Coming to the second problem. So here the section is already given and the length is already given. We have to find out the design compressive strength of the member. So when this is a built up member is given, we have to find out the section properties. As this one is ISMC, two channel sections are there and one plate is attached with. So these are the properties of ISMC 400 according to SP61, and then you can see we have to find out the neutral axis of the built up section to find out the moment of inertia. Yes, this is a very simple way to find out the neutral axis, which is taken as x, right? A1x1 plus A2x2 divided by total area. So from here we have to find out the combined moment of inertia. See, this moment of inertia is for only for channel sections, but combined, that means channel along with the plate, we have to find out in this way, along z axis and along y axis. So now we can compare, as Iz is lesser than Iy, then we can easily say Rz must be lesser than Ry. So in this case, Zz axis is the critical axis and more severe comparing to Yy. So we have to find out the compressive strength along ZZ axis only. So that's why find out Rz is equal to root over of Iz by A, put the values and you will get Rz. And now coming to the final part, design compressive strength, we have to find out slenderness ratio 34.82. Then we have to check for buckling class. See, in this case buckling class will be C for both the cases, as it is a built up section. You can see it in table 10. For built up section, yes, this is the built up section. For built up section along both axes it is C. So that's why we will only calculate along ZZ axis. So for 34.82 slenderness ratio, from table 9C we can find out the FCD this much by interpolation, and finally put the value here and you will get the design compressive strength of the member. Third problem, we can see that here the section is not mentioned. You have to design the section. The load is given, the section must carry this much of load. Okay, so in this case few assumptions you have to take, like we have taken some assumptions according to table 10, that the buckling class will be along ZZA and along YYB, and if this thing happens, then YY will be, Ry will be less than Rz. This is also an assumption, and critical section will be along YY axis. And again we have to assume the slenderness ratio, take it from 100 to 150. Alright, so here we have taken the assumed slenderness ratio 100, and as along YY the buckling class is B, we have to go to table 9B, and for 100 slenderness ratio we are getting FCD 118. So from the same formula we know the value of P, that is 1000. We know the value of FCD, and we can find out the area. Area will be the required area for the section we are going to choose. This is the required area. Then we have to go to SP61 and we have to find out the sections which have the area more than this one. And so along the observation, after the observation we can find out ISHB 350, which has the area 8591, which is greater than area required. And now for this thing we have to check the slenderness ratio along both the axes, YY and ZZ. Yes, we have to write down all the properties first from SP61. Then we have to check the buckling class from table 10, and this is the buckling class of the chosen section, and then we have to go to the design compressive strength. Okay, so here we have done the compressive strength along both the axes, because in the question you must have noticed that the length of the member is not same along both the axes. So it is 7 meter with respect to Z axis and 5 meter with respect to Y axis. So in this type of cases we have to find out the compressive strength about both the axes. So here first we did with along ZZ axis. So as the buckling class is A along ZZ, from table 9A for for slenderness ratio this much, we can find out the FCD by interpolation and simply find out the design compressive strength, and yes, it is greater than 100, so it will not fail along ZZ axis. Similarly along YY axis buckling class is B, so go to table 9B and find out the FCD by interpolation and put the value of FCD here, and you can find out the design of compressive strength, and yes, it is also greater than 1000 kilonewton. So from both the axes the compression member is safe. Now coming to the next problem, This problem consists of one angle section. So when it is angle section, I have already told in the previous lecture that the formulas will be a little bit different. As the main formula is same, PD is equal to AE into FCD, and the area of this angle is this much from SP61. And this formulas you can get from this clause 7.1.2, 7.1.2.1. And for angle specially we have to use this formula which is given in 7512. Now we can find out the value of K1, K2, K3 from table number 12. As in table number 12 the values of K1, K2, K3 is given for 2 bolts and both ends are hinged. So if this is given in the question, then no problem. If it is not given in the question, then you have to assume it. Alright, so if you get the value of K1, K2 and K3, then put the value of lambda VV and lambda phi. These formulas are also given in the same clause number. Yes, you can see here in the clause number 7512, this is the lambda E value. K1, K2, K3 is given in table number 12. These are the values of K1, K2, K3, and the value of lambda VV and lambda phi is given here. Lambda VV and lambda phi. Again go to the problem. So you have to put the values here. Mind it, very important thing is RVV. RVV is basically the minimum radius of gyration which you will get from SP61. Okay, for the particular section, take the minimum value of gyration. You will get 4 number of values. So among them the minimum will be the value of RVV. Then this B1 and B2 are the legs of the section, and this T is the thickness of the section. Alright, so after getting this value, put it in the formula, you will get lambda E. Then again put the value of lambda E and put the value of alpha. Alpha is given in table number 7, 0.49. Alright, for the buckling class C. So put the values here, you will get phi, and put all the values of phi and lambda E in the FCD formula, you will get FCD. Alright, so finally put the values of FCD, you will get the design compressive strength. Okay, so in this type of problem where single angles are given, you don't have to go to the table 9, table 8. Directly from the formulas itself we can find out the design compressive strength. The last problem for this video, here the section is not given. The angle section you have to decide, you have to design. The load is given, the section should take this much of load. Alright, so let us see, for this type of design problem we have to assume the slenderness ratio first. Yes, again like the previous problem we have taken 100, and for 100 the buckling class for angle section is always C. From table 10 you can see. So we have to go to 9C, and for slenderness ratio 100 you will get the FCD. Put the value of FCD, you will get the required area. So then we have to go to SP61, and for from SP61 we have to find or select a section which has a greater section than the required area. Right here we have chosen ISA 65 into 65 into 8, which has the greater sectional area comparing to area required. Okay, then for this angle section, RZZ means the minimum radius of gyration is 19.6, and again for compressive strength we know that 0.85 will be the into the length will be the effective length. It is given in clause number 7521. Yes, in clause number 7521 you can see it is given the slenderness ratio, the effective length will be 0.7 and 0.85 times, so the maximum value we will take. That's why the effective length will be 0.85 into this one. Find out the slenderness ratio and go to table 9C. Find out the FCD by interpolation. Put the value in the PD formula, and finally you will get the design compressive strength. Hope you can understand this problem. Thank you.